Yeah, let me know if you're coming. So. So after spending a little while telling you about the root poset and about small roots, let me make sure this thing is recording. So I told you about the root poset, I told you about small roots. I told you the key fact about small roots, which is that the number of them is finite. And so using these facts, we're going to show today this very nice result that Coxeter groups are automatic. And I'll explain what this means, but that's the goal for today. So let me tell you about automata. So if you have some set and you consider any subset of the set of words, so A star denotes the set of all finite words in this alphabet. So we think of this as the alphabet. A star is the set of every possible finite word made out of letters in this alphabet, and we're considering some subset of words. And so this is called a language. Okay. Now, so let me tell you what an automaton is. This word is hard for me to say. An automaton is a finite graph, a finite digraph. And so when I say digraph, I mean it's a graph where each edge has a direction. Either a forward edge or a backward edge. It's a finite digraph with a designated start vertex and whose edges are labeled by elements of A. Okay. So we saw an example already, which is this graph, where this guy is the start, and we have labels on the edges. So maybe my alphabet is A and B, and so maybe this is A, B, B, A. Okay. And so we say that an automaton recognizes the language L given by basically the words that you can obtain by starting at the start and walking around the graph and reading the labels you encounter. So words obtained from walks starting at the start vertex. Okay. In other words, for each automaton, there is a language that corresponds to it, and we say that that's the language recognized by the automaton. Okay? So in this case, we did this already. We basically saw that the words that we can obtain here are basically you either start with A, and then you can go B, A, as many times as you want, or you start with B, and then you go A, B, as many times as you want. And so the words you can obtain are basically the words of this form. Of length n for n greater than or equal to 0. Okay? This is the language recognized by this automaton. Okay? And maybe the first question you're going to ask when you have this situation is now, if I give you a language, is there a graph, is there an automaton that recognizes it? Okay. When there is, we call it a regular language. Okay. So such an L is called regular. Okay. So a language is regular if it is the language recognized by an automaton. Okay. And the first question you should ask yourselves is, basically, is every language regular? And you would imagine that if I bother to make this definition, it's because not every language is regular. And so let me give you a simple exercise, which is to show that this language, the language of words of the form A, B, 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 where this appears n times and this appears n times, and you let n range over the positive integers, is not regular. So you should convince yourselves that it's impossible to build a finite graph for which these are exactly the walks in that graph. Okay? Okay. So are these definitions clear? Is it clear what a regular language is? So the main theorem of today, as you can probably anticipate, is that the language of reduced words of a Coxeter group is regular. Where again, I want to assume that this is a finitely generated Coxeter group, because if it's not, then there's just no hope of this being true. Okay? So any finitely generated Coxeter group has a regular language of reduced words. Okay? In other words, I need to build a graph like this. So let's do a little warm-up here. Which is the case W finite. Okay? Now, the first thing I'll tell you about this warm-up is that you should be completely unimpressed by what I'm about to do. Why? Because if the group is finite, you can easily convince yourself that there's only finitely many words in this language. And if there's a language with finitely many words, I think you can build a graph that basically has those words as the walks. Okay. So this result is just trivial when W is finite. But anyway, I want to talk about it because I want to build a nice graph with this property. Okay. And actually, we have a nice graph. So let's do this for S3, which is one of our favorite examples. And we have a very nice candidate, which you guys know very well. It's this graph. We've drawn it over and over many times. So this right here is the Hasse diagram of the weak order. Okay. And we know that the weak order comes with a labeling on the edges. Right? And basically, we know that if you want to know what this element is in the group, then all you have to do is read the labels up and go A, B, and then this is going to be the element AB. This is the element A. This is the element B. This is the element BA. This guy has two different reduced expressions, ABA and BAB. And this guy has the empty expression. Okay? And so the weak order, if I just direct it up, is exactly going to be the automaton that I need. So the weak order will do. Weak order oriented up will do. Okay. But I want to think about this a little bit more carefully. And I want to do this in an equivalent but slightly different way. Okay. So what I want to do is the following. Let me draw the same graph but label it differently. What I want to do is thinking about the root system that corresponds to this picture. So we know that the root system has alpha and beta as its generators, as the simple roots, I'm sorry. And then here's gamma, and then minus gamma, minus alpha, minus beta. That's the root system, right? These are the positive roots, alpha, beta, and gamma. And let's put in the reflections A and B. So A acts by this reflection, and B acts by this reflection. Okay? And what I want to do now is make this same picture, but now instead of labeling by the group element, I want to label by the set of roots that that group element makes negative. Okay? I know that these guys, that the bottom guy makes 0 roots negative, these guys make 1 root negative, these guys make 2 roots negative, and this guy makes 3 roots negative, and I want to just write down those sets. Okay? So for example, this guy makes the 3 positive roots negative, so that's the top element, and it makes alpha, beta, and gamma negative. The bottom element makes no one negative, so it's the empty set. Now, who does A make negative? Well, I know that A makes exactly one of these positive roots negative, and it's the corresponding one, alpha. Right? B makes beta negative. And so really the only ones that I have to do a little bit carefully are these two. So who does AB make negative? It has to be 2 out of the 3 roots, right? So which ones are they? Well, you just have to do it. So, for example, let's consider alpha. So what does AB do to alpha? Well, here's alpha. B makes it into gamma, and A makes it into beta. So AB times alpha is beta. That's not negative, it's positive. So that means that alpha is the one that doesn't go here. And beta and gamma are the ones that go here. Okay? And by symmetry, alpha and gamma are going to be the ones that go here. And so let me draw the same graph, but with this labeling now. But let me keep the edge labels intact. Okay. I'm taking a group element W, and I'm sending it to neg W, which is going to be the positive roots that W makes negative. Okay. So what I want to say is that basically, I mean, let's think about this for a second. Our hope is to do this for infinite groups. Now, this is clearly not going to work for infinite groups, right? Because, I mean, I can do exactly the same construction. The infinite groups have a weak order, but this is an infinite graph. Okay? And I don't right away see how to generalize this. Okay? To how to adapt this to the infinite case. Now, I take this picture and I make it into this equivalent thing. Okay? Now, what happens when I try to do this for an infinite group? Well, if you think about it, I still have one node for each group element. So this is also infinite for W infinite. Okay? So this is not going to generalize right away. So what I'm going to do is I'm going to adapt this construction. But this is going to be a better point of view than this one. Okay? What I want to understand, first of all, is if I forget what in other words, I want to understand what this graph looks like. Okay? So what I want to do is the following. I want to understand if I have some set here. Let's say that it's alpha 1. Or let me call these gammas. So in this graph, let's say that I have gamma 1 up to gamma L, let's say. Now I have some label here, Si, and I would like to know what goes here. Okay? But I don't want to have to translate back to the Coxeter group. I really want to just look at this, and immediately know what to put right here. Okay? So if these are the roots that W makes negative, what are the roots that WSI makes negative? Okay. Can you just, looking at this, tell me what to put in this box? Can you tell me some of them? Now remember, how many roots are here? Well, we know that it's exactly the length of W, right? So the number of roots that go here is the length of W. I'm multiplying by Si. I'm becoming bigger. So this thing has length of W plus 1 elements. So I need to put length of W plus 1 things in here. And I need to somehow build them from here. So any ideas of something that can go in here? I see some of you guys mumbling it but not saying it. See, what happens if I take Si gamma 1? What does WSI do to this? WSI multiplied by Si gamma 1, the Si's go away and I get W gamma 1, which is negative. So that means that Si gamma 1 should go here. For the same reason, all of these guys should go here. And now I'm just missing 1. So what's the other root that becomes negative? I'm going to show that it's alpha I. Why is it alpha I? Because I need to check that this is negative. I claim this is negative. I know that Si alpha I is minus alpha I. So this is minus W alpha I, I'm claiming that this is negative. In other words, I'm claiming that W alpha I is positive. Why is the W alpha I positive? Because WSI is bigger than W. Okay.
So that's how we know alpha I wasn't already in your other set?
That's a good point. That's how I know that alpha I is here. But how do I know that it wasn't one of these guys that I just put here? So how do I know that alpha I is really different from these guys? Well, let's suppose that it's not. Suppose that alpha I is equal to alpha Si gamma j. So how am I going to discard this? Well, if this was the case, then gamma j would have to be, what's the thing that Si sends to alpha I? Gamma j would have to be negative alpha I. Right? But that can't be because these are positive roots. So that shows that alpha I was not one of these other guys, and so it is the last missing one. Okay. And so this is very handy because it tells me that I can do this. I can go from here to here without actually doing any kind of going back to the group. Okay. Let me write this in symbols. What did I just prove? I just proved that the negative set of WSI is obtained from the negative set of W by taking all of these guys and multiplying on the left by SI. Okay. And then adding alpha I. Okay. Any questions about that so far? So what's the point? The point is that if I'm walking around this graph and I am at a certain vertex and I know what edge label comes out of it, then I know what vertex I'm headed to. And I can do it using this computation. Okay? Now the trouble is that I have infinitely many vertices here. Why? Because there is infinitely many roots. Okay? And so I might just try the crudest thing that I could possibly try, which is to say, well, I don't like this infinite set of roots. What if I try with a finite subset of them? So why don't we try with the small roots? And we try to do the same thing. But whenever we see roots that are not small here, we just knock them off. So let me go ahead and do this. So instead, so now for W infinite, what I'm going to do is we're going to instead do the same thing. But now instead of considering all the positive roots, I'm only going to consider the small roots. So these are some of the positive roots. Okay. So now I'm going to think that for each group element, instead of labeling by all the positive roots that this element makes negative, I'm just going to ignore the large roots that appear here and focus only on the small roots. So I'm just going to focus on the set of small roots that W makes negative. Okay. Now, as I told you, a lot of the trouble with doing interesting examples for small roots is that in a finite group, every root is small. So if I were to do this example for S3, I would do exactly the same thing. Okay? So I'm going to do this in an example for an infinite group. But what's the key property? The key property is the following. And this is the key property of the situation. It's the following, that if I have some set of small roots. Well, let me first write it in symbols. If I want to know which are the small positive roots, the WSI makes negative, it turns out that the formula looks exactly the same. It looks exactly the same, except that these guys are all supposed to be small. And so all I have to do is intersect with the small roots. Okay? So in other words, so this is for WSI bigger than W. Okay? So in other words, if I have a group element, and I know that these are the small roots that this group element makes negative. And now I would like to know which are the small roots that this guy makes negative. Well, it's basically just doing exactly the same thing. With one difference, which is that maybe I took these small roots and I did something to them, maybe they're not small anymore. And if they're not small anymore, I just cross them off. So I just cross off non-small roots. Okay. And I'm going to build exactly the same graph, except keeping track of only the small roots. So let's do an example of this. So here's an example. The affine Coxeter group A2, it corresponds to this picture right here. We know this group is infinite. It's one of our favorite infinite Coxeter groups. Now, do you guys remember what this root poset looked like? It was kind of like this. It looked like a braid like this, and then like this. And then a braid like this, and then like this. And it kept going to infinity. And if you remember, these guys were the long edges. And so we said that the small roots were these 6. Okay. So my small roots are alpha 1, alpha 2, alpha 3, alpha 1 plus alpha 2, alpha 1 plus alpha 2 plus alpha 3, and alpha 3 plus alpha 1. Okay? And so I start and I do exactly the same construction as I did over here. Okay? I'm going to do the same thing, but whenever I find roots that are not small, I just forget about them. So let's start. So I start with the empty set. Okay? And in the back of my brain, I think, okay, this empty set represents the identity element. Okay? Now, how can I make the identity bigger? Well, I can multiply by any of the three simple reflections, and I'm going to get bigger. So I'm going to have an edge S1, an edge S2, an edge S3, right? So let's start with S1. What am I going to get here? Well, I just apply that rule that we all should copy it in this board so that it shows up in the video. So what I do is that I take, if I want the roots in my new node, I take the roots in my old node, multiply them by Si, then I add the root alpha I, and then I delete large roots. So let's do that. First, take the roots in the old node, multiply them by Si. Okay? Well, in the old node, there were no roots, so I have nothing to multiply. There's no contribution from that here. Then I add alpha I, which in this case is alpha 1. And then I erase large roots, but I don't see any large roots, so I just stop there. Okay? So here's alpha 1. And again, you should be thinking in the back of your mind that this now is the group element S1. Okay? Now, how can I make this bigger? Well, either I can multiply by S2 or by S3. I can't multiply by S1 because I'll become smaller. So let's multiply by, so that means I have edges going out of here from S2 and S3. Okay. Let's do this one first. So what am I supposed to put here? Well, I take the things that were here, and I multiply by S2. So what's S2 of alpha 1? I'm gonna have to remind you what that is because I can't remember. You have to do it. So we did this last time, and so when we did this example, we actually figured out how S1, S2, and S3 acted on the roots. And I'll just remind you what they do. What Si does is that, of course, if you act on alpha I, it gives you negative alpha I. If you act on alpha j, it adds alpha I to it. If you act on alpha I plus alpha j, well, that means you take this plus this and add them, which means that you get alpha j. And if you act on this, then you get 2 alpha I plus alpha j plus alpha k. Okay? So this is a complete table of how the generator Si acts on the small roots. This is what it does to them, and these are the computations we're going to have to do over and over here, so it's good to have them in a little box here. Okay? So let's go back. I was saying that I needed to compute S2 alpha 1. S2 of alpha 1 is alpha 1 plus alpha 2. So I put that here. So that takes care of this part. Now I'm supposed to add alpha I to this, which in this case is alpha 2. And then I'm supposed to erase the large roots, but there aren't any large roots. So that's good. And that tells me that, and in the back of my mind, I think this node corresponds to the group element S1, S2. Let's continue. How do I now make this bigger? Well, I can make this bigger by either multiplying by S1 or by S3. Okay? So you see this is going to branch out. This is a big picture. But I want to do a good part of it. So what happens when you put S3 here? Well, you're going to get some other node. Okay? And then you say, OK, well, first, I make S3 act on these things. So S3 acting on alpha 1 plus alpha 2 gives me alpha 1 plus alpha 2 plus 2 alpha 3. S3 acting on alpha 2 gives me alpha 2 plus alpha 3. And then I'm supposed to add alpha 3. I take this. Now I'm supposed to knock off the large roots, and now for the first time I see a large root. Okay? So that means that this thing goes away. And I just get alpha 2 plus alpha 3, comma, alpha 3. Okay? And again, you think this is the group element S1, S2, S3. You basically keep doing this. Now, is there an end to this? There is an end to this. Why is there an end to this? You see, what are the things that I'm putting in these circles? They're all subsets of the small roots. Yeah? The small roots are finite in number. That means there's only finitely many sets. And that means that this might be a long process, but it's gonna start cycling into itself because there's only finitely many nodes in here. Okay? Maybe you can see already how a cycle is about to form. Can you see? There's some symmetry here. Alpha 1 plus alpha 2 goes to alpha 2 plus alpha 3, alpha 3. So by symmetry, if I now take S1 and I make it act, what am I going to get? Well, I'm going to get, what am I going to get? The alpha 2 became an alpha 3. The alpha 3 is going to become an alpha 1. And this is going to become alpha 3 plus alpha 1. You do it carefully. I'm telling you, when you do it carefully, you get this. Okay? And again, by symmetry, if you now put S2 to act on this thing, I'm going to land back here. Okay? And so this is how cycles start to form. Now there's other things coming out of here. Right? It's a big graph. But I want you to notice that this fact that cycles form is completely different from before, because before that was the weak order. It was a poset. Okay? And in posets you don't have cycles. But here you have cycles. Okay? And you see that has an important implication, which is that I'm telling you that you should be thinking of these as group elements. Right? So what's this group element? Well, it's S1, S2, S3, S1. So what's this group element? Well, it's S1, S2, S3, S1, S2. And you see, actually, these two group elements are different. You cannot reduce this and get this. And that's the key thing here, which is that a node is going to represent several different group elements. Yeah? Which is how we're going to get away with taking this infinite group that has infinitely many elements, and we encode it into finitely many nodes, because each one of these, or some of these nodes at least, are going to have infinitely many things stacked on top of them.
So the nodes correspond to subsets of...
So each node has some set of reduced words. It represents some set of group elements.
I mean, so the nodes in this picture are actually we're going to have 6 factorial.
Actually, well, let me go back to that question. But maybe the next point I'll make is that before, each node represented one group element. Here, each node represents possibly many, possibly infinitely many group elements. Okay? What we have here now is a map from W to the subsets of the small roots. Now, here this was a nice injective map. Here it's kind of a mess. What am I doing? I'm taking each W and I'm sending it to this set. Okay? And there's a lot of questions that you should be asking here. For example, what's the image? Is the image everything? Isn't that a commercial? Image is everything. Is the image everything? Is this? I mean, you can imagine that it's not, right? Like already here, the image is not everything. You don't see the single set gamma. You don't see alpha, comma, beta. But you can ask yourself, what is the image? Or for example, you can ask yourself, what is it that I have stacked on top of each one of these guys? These are called the fibers of the map, right? All the different group elements that map to the same thing. So what are the fibers? Phi. Actually, I shouldn't use phi because phi is the set of roots. Let me use F. What are the fibers? F inverse of some set. Okay. Are they all infinite? Are some of them infinite? As I understand it, this construction is about 10 years old, and I looked and I couldn't find any answers to these questions, and these might be open questions. So is this open? Maybe. These may be open questions, and they may be open questions that you can understand. For example, in special cases like AN, I expect that you're going to get very nice answers here. And so if you're not too satisfied with the project proposal that you're about to turn in, you might switch it to this. I don't know. I mean, I think these are really nice questions that I don't think are fully understood. Okay? But my point is that this is the automaton. This is what does it. And actually, with the work that we have done, the proof is not hard as long as I don't erase my claim. So this claim is the same as this claim right here. And I will now prove to you that the claim implies the theorem. So the automaton is this thing that I just built. Vertices are the sets of the form negative sub sigma of W for W in my group. Okay. What are the edges? Well, basically what I do is, if I have some set S here, first of all, when should I or should I not put an edge with the label SI coming out of here? Okay. In other words, why do I have S2 and S3 coming out, but not S1? Well, basically, I need to know, when I multiply this group element by alpha I, will it be positive or negative? And how do I settle that? Well, I settle that by looking, is alpha I here or not? If alpha I is here, then W alpha I is negative, which means that I'm becoming smaller. So I don't put it in here. If alpha I is not in this list, then multiplying it makes me longer. So I have an arrow SI coming out of here if and only if alpha I is not in this set. Okay. And just from knowing, let me call this A because S means something else. Okay. If I tell you A and I tell you SI, then you know right away what you're supposed to put here, even though you don't know what group element I might be having in mind at this moment. What you have to do is take SI multiplied by A, add alpha I to it, and intersect with the small roots. Okay? That's my automaton. In other words, it's exactly what I just did. So why is this automaton one that recognizes my language? Well, what do I need? I need that S1 up to Si is reduced if and only if it is a walk in the graph. Let's call this graph G. Okay? And I'm going to show to you that that there's not much to say here. So we proved this by induction on I. So for I equals 1, this is pretty trivial because every single generator is reduced, and we have, from the empty set, we have arrows S1, S2, S3, one for each generator. So I equals 0 is OK. And now let's go from I to I plus 1. So how do I know if this thing is reduced? S1 up to Si plus 1. Well, I have to make sure, first of all, that this is reduced. And second of all, that when I multiply by Si plus 1, I get longer. In other words, that when I make this act on alpha I plus 1, I get something positive. Okay. Now, if and only if. When is S1 up to Si reduced? Well, by the inductive hypothesis, there is a walk with edges S1 up to Si. Okay? So here it is, S1 up to Si, and now I'm standing over here. Now, this guy is one of the group elements that corresponds to here. So if I want to know if alpha I plus 1 is positive, all I need to check is whether alpha I plus 1 is sitting in this box or not. I need alpha I plus 1 to not be in here. Okay? But what does it mean for alpha I plus 1 not to be in here? It means exactly that I have an edge Si plus 1 coming out of there. So I have a walk like this, S1 up to Si. And I have something here which has no alpha I plus 1 in it. So that means that I have an edge Si plus 1 coming out of it, and I have my walk S1 up to Si plus 1. And that finishes my proof. Okay. So you see, basically, once you come up with the right construction, the proof is really fairly straightforward, except that there's one key thing that I haven't proven to you, right? Which is this clean. And this is, of course, the key thing, and it's the impressive thing. The impressive thing is basically that this result is due to Brink and Howlett. And the impressive thing is that they managed to find a set sigma that is finite, but which has this same behavior that the infinite set has. Okay. And this is really the most impressive part of this work, is coming up with the correct concept of small roots so that they satisfy this property, and there are finitely many. There's finitely many of them. Okay. And so next time I'll prove this to you, but you'll see even the proof of this is not too bad. The main thing is just the fact that they managed to come up with the small roots. And Giancarlo Rota used to say that a good definition is much, much better than a good theorem. And I think this is an example where these guys came up with the right definition, and that kind of makes the theorem go through. Okay. All right, stop there.
ones that actually give you
overlap. And it could be I just need to turn off a little down because I lost execution, or it could be that they say that I don't know.
I normally just do it until my memory says, hey, you don't have memory anymore, and it shuts my computer off. Program down. So, which is normally quite a few.
By the way, I didn't tell you, but if you want to see the full picture, it's in the book, page something or others.
119.
119. It's not much
Something
bigger
like
than this
that.
actually. I think it has like 12 notes or something like this.
Again, it seems to me that you or I are going to be somewhat biased on what we choose to
I think that's all. Well, I was using random triangles.
I mean, you're using random triangles. I'm using random triangles. Our random triangles are going to be different than if you actually just generate them. Kind of a preconceived notion.
Well, and I think that kind of helps me. Like, we do have different opinions on this, because otherwise, because like, oh, look, it works. We're really chicken buttons, and that would
Right.
make us so
I think it's going to be helpful to have something that doesn't have that preconceived notion.
Right.
Just picking
What, did you not see the email from me?
Right.
So,
So yeah, I'm going to try to get Mathematics 6. I'm going to have it for here on my desktop.
if you think
And,
that's the worst, because the one I got wasn't magically working. And that's what I solved and got magically working.
gotcha.
So if you solve that problem, you let me know.
I can probably solve that problem.
Okay. I was having some other issues, so, you know.
You gonna talk with Zoe
I
about
just got to
theory?
figure out how I'm going to program this thing.
Well, the book I picked up, I think might actually work with Mathematica 5, which is actually working on my desktop.
Everybody needs
This
batteries.
book weighs more than I do.
Way too many.
You just told me this book weighs more than I do. I'm
It probably
this
does.
could be a problem.
Next pedal, same thing.
But I think that it'll be okay.
So I remember something that I meant to tell you guys. Another good special case
Uh-huh.
that you might think about.
How you leave and plugged in now.
Uh-huh.
It's the regular simple higher dimensions. You might start with the regular simplification first.
Uh-huh.
I think that's a good case, which is harder than the lateral triangle, but I think it's easier than a general triangle.
So you mean just tiling the
For example, the
plane with like
three-dimensional space
uh-huh.
by reflecting at the even or
Okay.
Okay. I'm having enough trouble drawing the triangles.
Right.
so it's harder to draw, but I think it might be easier to prove once you figure it out. Maybe. Not entirely sure, but
Sounds possible.
Federico, is it okay if I just, because I didn't get a chance to print up my project proposal before I got here.
sorry, say that again?
I didn't get a chance to print up my project proposal.
Where did you look?
So
What are you guys doing in the